So question 2 is about predicting the products at which and which electrode they are produced at in an electrolytic cell containing. Okay, so we're going to first predict aqueous sodium chloride. So the fact that it's aqueous means that it contains water. It's in a water solution, so that's going to interact with the electrolysis process. And we've got sodium chloride. We're not really told what concentration the sodium chloride's at. I'm just going to assume it's at 1 molar. So I'm going to find each of these ions. So sodium chloride contains sodium ion and it contains chloride ion. So I like to start off with a drawing just because it makes it easier to understand. So here we have the electrodes and they're inert. The question really doesn't say that there's any other electrode other than inert, so we're just going to assume that they don't get involved with the reaction. Okay. So we've got this kind of setup. Now, I'm just going to make this the negative side of the electrolytic cell, and I'm going to make this the positive side. It doesn't really matter at this stage which one's which, because your reactions will change depending on where the electrons are flowing. So because this has become the negative electrode, that means that electrons are flowing that way. So they're actually going to be storing within the metal here. So there's going to be a whole stack of electrons storing there. And out of this side of the electrode, you have electrons flowing towards the positive terminal of your battery. So this side here is called your cathode because that's where electrons are going to be gained. The battery determines that. And on this side, this is where electrons are being lost. So it's your anode. Okay, now we have to predict what happens at the cathode and what happens at the anode. So I'm just going to determine where each of these equations are. So because it's a solution, we need to consider water. We also will need to probably consider this water down here and the sodium right here. Okay, so we've sort of got all the reactions written down. Now at the cathode, remember the cathode is where looking at what chemical is the location of reduction. So it looks at which chemical is going to gain electrons. Now neither of these chemicals up here are capable of gaining electrons. It's only going to be these two down here. Now we know that when water and sodium ion compete, water is going to be better at gaining electrons because it's higher on your electrochemical series, making it a stronger oxidant. Okay, so water is a stronger oxidant, sodium is the weaker oxidant, sodium ion, and so water is going to be the reaction that takes place at the cathode. So I'll just write it out. So we have two waters within the solution gaining 2 electrons off this cathode here and forming hydrogen gas and 2 hydroxide ions. Okay, so you've got hydrogen gas that will be bubbling around here, and that will be the formation of hydrogen gas at the cathode. Okay, so next we need the anode. Okay, so the anode is where electrons are being removed. So it's actually easier to remove water's electrons rather than chloride's electrons, because chloride is slightly higher up on the electrochemical series. Chloride ions are not as strong of a reductant as water is. Okay, so this water equation will be the first one that lets its electrons go. So 2 waters will turn into oxygen gas plus hydrogen plus 4 electrons. So that will be the equation that takes place at the anode. Now, in terms of, I guess, the overall redox reaction, what we have is we have the cathode that needs to be multiplied by a factor of 2. And so we've got 4 water liquids plus 4 electrons forms 2 hydrogen gas molecules, 2 OH minuses, and then we've also got the anode equation, which is just going to be 2 waters. No, we'll get rid of this. 2 waters converting into oxygen gas plus 4 hydrogen plus 4 electrons. Okay, so we're adding these 2 up together, and so we will get 6 waters forming. Now, what we'll have take place here is we've got 2 hydrogen ions. I'm just going to cross out the electrons because they are produced on both sides of the reaction. So 2 hydrogen, yep, that was meant to be gas. 2 hydrogen gas molecules plus oxygen plus, now the 4 hydrogen ions here and the 2 OH ions here, did I double that? Yes, I did, so that should be 4. Now, that's going to form 4 waters. Okay, and so what can happen is that because you have 6 waters at the beginning and 4 waters as a product, you can cancel them out, and basically you have 2 waters turning into 2 hydrogen gas plus oxygen gas, and this will be your overall reaction. Now, to work out the voltages, you have to figure out, what the voltage of the oxidation half equation is. So we know that the oxidation half equation, that goes backwards, and so wherever it is here, that's negative 1.23 volts, and the reaction, this reaction here, just from the electrochemical series, it is negative, once I scroll down, it is negative 0.83. So it's given to us here. So the overall voltage is, you simply have to add them up. So 6, hang on, so 6, yep. So we should get negative 2.06 volts. So we need a minimum of that amount of volts for electrolysis to occur. Okay? So that's that first question. Now, getting rid of these, I'm just going to get rid of these. So with electrolysis, it's all about thinking about, which side gains electrons, which side loses it, and then obtaining the overall reactions. So, I just drag this down a little bit. So we have molten lithium iodide. Now, molten lithium iodide, the fact that it's molten means no water. So water is not going to interfere. So we know that we have lithium iodide, which is Li. Now, that breaks down into the following ions. So you can still get them as ions. It's just that they're not going to be in aqueous state. They're just going to be in liquid state, the ions. So it will be lithium as a liquid and iodide also as a liquid. So you won't be placing aqueous because aqueous means immersed in water. These ions are simply just melted and they exist in solution, but the solution is not water. So let's find those two chemicals. So we know that we have iodide, which is somewhere, I saw it just a moment ago and now I can't see it. Okay, it's up here. That's the voltage. And then we've got the other equation, which is lithium, down here. So in the electrolysis of this solution, so if I just, it's not a solution, it's a molten solution. If you just have these two electrodes, I'm making my diagram smaller and smaller, but I guess this is a slightly easier question because you won't have the interference of water. So here, let's make this the cathode, and this here can be the anode. So at the cathode, we have the gaining of electrons, okay, because it's reduction. The polarity of electrolysis at the anode is always going to be negative. And so the reaction that takes place there at the cathode is that lithium plus electrons is going to turn into lithium solid. So it's only lithium that's possible in gaining electrons. We can see that iodide can't gain electrons. Okay, it's already gained electrons, it's already I minus. So it can only lose electrons. This is liquid phase. So that's the cathode equation. The anode equation is two iodides in liquid state are going to form iodine solid and two electrons. So that's what's going to happen at the anode. So there's going to be an accumulation of iodide on this particular anode. So at the anode you have a collection of iodide solid. It may or may not stick on the actual electrode, whereas the lithium will be built up here on this. So here you have lithium forming. So it won't be that exaggerated, but I'm just for illustration purposes. So that will be lithium solid being gained there. Now the reactions that take place, I guess you can go straight to the overall reaction. In the anode there are 2 electrons produced. In the cathode there needs to be 2 electrons absorbed by the lithium ion, so we need to double that equation there. So overall reaction is going to be 2 lithium plus electrons, 2 electrons that form lithium, 2 lithium solid, and then we have 2 iodide plus I2 solid. That produces I2 solid and 2 electrons. So when you add those 2 reactions, you have 2 lithium iodide molecules, probably in their molten state, melted, the electrons are going to cancel out, and you'll have 2 lithium plus I2 solid forming. So this is going to be your overall reaction. Now, in terms of finding what the value of the voltage required is, you need to take the lithium equations, half equations, so read it from the table. It's negative 3.04 volts. It's found right there. And then we know the iodine equation is this, but it's been flipped around, so it's actually negative 0.54 volts. And so the overall EMF requires 3.58 volts of potential difference. Okay, so I'll just write requires that amount of volts. And that's the minimum amount. You need to have more than that because you won't have 100% of the voltage if you just have that as the amount provided by the battery. So it always needs to be exceeding that value. Okay, so let's have a look at these last 2 questions, and that way it will give you better understanding of predicting these. So molten tin sulfide. So we can go, I think now we can sort of avoid drawing diagram because we've already done it a few times. So we're getting more efficient at hopefully working these out. Now what I'm going to do, I'm going to find molten tin sulfide. So tin, where is it? Here it is. Tin 2. Okay, so remember that that's SN2+. Sulfide, not going to be, it's a spectator ion. So it's just essentially tin in the reaction. Now, there are 2 equations for tin. There's this one here, and there's also this one up here. Okay, so this is a bit of a trick question. Now, so if we do have the anode, at the anode, the reaction that's gaining electrons is going to be, well, it can only be tin 2+. Sorry, at the anode is going to be losing electrons. So it can only be this tin up here breaking down into tin 4+ plus 4 electrons. Because remember, at the anode you have oxidation. And this is molten, so there's no water to take into account, there's just liquid. So that's at the anode. And then we have the cathode, which is where electrons are being gained. So we know that that has to be tin plus 2 electrons forms tin solid. Liquid. And so we've got these 2 reactions that are taking place. And so what we can do now is just fuse them together. We do need the voltages probably. So this one up here, it got flipped around the other way. So it's going to be negative 0.15 volts. And this one here is proceeding as it has the same voltage. It hasn't really flipped around. And so the overall reaction that takes place is going to be tin 2+ plus another tin down there, which we're going to add in a moment, form tin 4+ plus tin solid. And I'm just going to write this as, instead of writing them separately, I'm going to write this as 2, so adding 2 tin ions. And the overall voltage required will be negative 0.29 volts. That's how much voltage will require for this reaction to take place. Okay, so finally we've got aqueous iron 3 oxide. So iron 3 oxide, iron 3 and O2 minus, and it's aqueous. So we've got H2O as well taking place. So let's have a look at spotting these on the electrochemical series. Now, I might get rid of, once I can find this rubber. Okay, I'll get rid of these. Now, we have to find oxide. Don't know what these random things up here are. Just get rid of them too. So we need to find our water, so we know it's there. We also have iron 2 plus. No, iron 3 plus. So we need to find iron 3 plus. There it is. And then we have, do we have any more iron 3 plus? Well, we have this water to consider. And we don't have oxide on this electrochemical series, so I don't think we'll need to worry about it. If they do happen to provide an electrochemical equation for it, then a half equation, then yeah, you might want to worry about that. But in this situation, just based on this electrochemical series, there's no need to worry about it. So those are all the half equations that I can find. Now, the one that would be at the, so we've got two equations competing. The water equation that will be trying to grab electrons, and this iron 3 plus equation that's going to try to grab electrons. So obviously, because the iron one is higher than that bottom water, that one is actually going to be the one that will gain electrons. So that will be the reaction that takes place at the cathode. Whereas this water equation is the only one that is providing electrons. So it's the only reaction that can be at the anode. So we know that the two equations that take place, iron is going to grab 3 electrons and is going to form iron solid, and this is going to be at the, because this is gaining electrons, so that's at the cathode. And at the anode, we've got water breaking down into oxygen, hydrogen ions, and 4 electrons. Oops, I shouldn't have made that solid. That's not correct. It's 2 plus, and that is going to turn into aqueous. So that's aqueous, and that's aqueous. And then we have liquid turning into 4 hydrogens plus oxygen plus 4 electrons, I believe. My memory is a bit bad. I'm trying to remember these. I should really understand them instead. So 4 hydrogens plus 4 electrons, yeah. Okay, so we've got this particular equation happening, and as you can see, I haven't changed that to a single electron. Now, so the overall reaction that will be taking place, so we've got iron, that this equation, the cathode equation, needs to be multiplied by a factor of 4 because we have to have 4 electrons being gained. There are 4 electrons being lost here. So we need 4 Fe3 plus 2 waters gives us 4 Fe2 plus 4 H plus oxygen. So that's going to be gas. That's aqueous. Liquid and aqueous. Okay, so in terms of finding the voltage, we need to just have a look at it from here. So that's going to be, because that's flipped around, that's going to become negative 1.23 volts, and we added to the 0.77 volts. Okay, so we're going to get probably something around negative 5.4 or something around that. I'm trying to do this in my head. So negative 1.23 plus 0.77, negative 0.46. So that was way off, but okay, let's just write it down somewhere there. So EMF is equal to negative 0.46 volts. So that's the potential difference that is required for this reaction to take place. And bear in mind that, once again, while these reactions are taking place, because you have a buildup of Fe2+, you may find that there begins to become there is an equation that takes place later on as you build up more and more Fe2+ ions, because it's a product here, so it can actually be a reactant. So there may be a spontaneous redox reaction occurring somewhere, but I don't think there is in this situation, because Fe3+ will still be the one at the very top that's gaining electrons, and Fe2+ is not as great at gaining electrons, so probably nothing will really take place. But you do still need to consider these things in the bigger scheme of things.